Hello and welcome to this lecture. In this lecture, I will be teaching you how to model methanol production from biomass, right? Methanol production from biomass. Now, in the last tutorial, we completed our biomass model, of which in this model, we produced hydrogen, right? We produced hydrogen. Now, we'll be using this model as a basis for methanol production. Now, methanol can be produced from syngas, right? And syngas can be derived from biomass gasification, right? So we'll be using this model as a basis for that particular process, right? So now, this is basically what we have for methanol production, right? So methanol production can actually be produced following these steps or procedures. You have gasification of the biomass, right? Gasification of the biomass. Then you have separation of syngas from other gasification products. Then you now have syngas pretreatment. Now what that means is you have your methanol production occurring at certain process conditions or operating conditions for pressure, temperature, right? So you have to take or set or modify the process conditions of your produced syngas to match those specific process conditions of which methanol is to be produced, right? Then you have your reaction of syngas inside your methanol reactor. Then you now have separation of methanol from the unreacted components that are left in the reactor, right? So when you get your reactor products, once you obtain your reactor products, you have to separate methanol from the unreacted components, right? So basically that's the steps, or those are the steps for methanol production. Now, for methanol production, you need a little amount of CO2 and H2O present in your reactor, right? So as you are feeding the syngas to the reactor, you would also feed little amount of CO2 and H2O, right, to favor or boost the production of methanol. And these two components are also components that are produced from biomass gasification, right? So you can actually get this from your gasification procedure as well, your gasification process, right? So you feed some of it with the syngas into the methanol reactor, right? So you have your reaction equation, right? Your reaction equation is this over here. So we'll be making use of this in our model. Now, for the reaction, conversion of syngas into methanol, based on research, is within the range of 60 to 90%. So we'll be making use of a value within that range in this particular model, right? So with that, we can move over to the simulation environment to quickly begin with the modeling, right? So we have this as our process at this point. So the first thing to do is to add methanol to the process. So we go to components and just type in methanol. Yes. So we just type in methanol, and then we can go back to the simulation environment. You can go back to the simulation environment. So you just add methanol to your process. Then what can we do next? Okay, so for this particular separator, yes, this separator, it's separated hydrogen from the other products. So what we can do is to adjust the splits that are here, right? You adjust the split. So we had only hydrogen coming out, so we can adjust it to also let CO2 come out from the top product as well, right? CO, right? CO, because syngas is a combination of H2 and CO. So we just adjust it to make CO come out from the top, right? The top of that separator as well. Also, we can add a little amount of water. Let me see. Okay, so it's CO2, yes. So it's CO2 and H2O. So let's say we use let's just use 0.05 for CO2 and also 0.05 for water as well, right? So just little amount of CO2 and water, right? So we can run the model. We run the model and then we check the products streams of this separator. So we can check the product stream of this separator. You have stream results. So from your stream results, you would see, let's see the mass flow. The mass flow, you have, yes. So you have CO coming out from this. Then you have H2 and then, yes, CO and H2. Then let me see, okay. Let me see if there is water. Okay, so apparently there was no water coming out from this particular separator. So I have to go and check where water is in this particular model, right? So checking from the last reactor, the last gasification reactor, to see if any CO2 is left. Let's see the stream results for CO2 and H2O. Let's check. So we have mass flow. So mass flow for CO2, you have some CO2 entering, but it seems like it's used up in the process, in the gasification process that produces hydrogen. And then let's check for water. Okay, for water, the same thing. Okay, so all the CO2 and water that is produced from the Gibbs reactor, is actually used up here in the gasification reactor, right? So I think we will just add the CO2 and H2O externally. Yes, because from the Gibbs reactor, some let me see, some CO2, yes, CO2 was produced in the Gibbs reactor as well as H2O, right? So yes, so we will just use an external source for that, right? So let's just continue with the model. So we can create a material stream to add CO2 and H2O, right? Yes, I think that's what we'll just do. CO2 and H2O, just little amount for each of them, just to boost the production of methanol, right? So just a little amount. Then we are going to use a mixer for them, right? So let's see, CO2, H2O. Okay, so CO2, let me specify. I'll just specify atmospheric conditions for this. Atmospheric conditions. I'm using mass flow. I don't want it to be so much, so I will just use 50 kg per hour. So this is just an assumption, right? So just use a very little amount of CO2 here, and I will do the same for H2O as well. So let me see. Okay, yes, this is for water. Yes, so I'm still going to use the same amount. And mass flow, let's check the mass. Okay, mass frac for water is 1. Yes, then we can send all of this through a mixer and name it. Okay, then let's see. Okay, so we have, okay, so we have our mixer outlet. The mixer outlet X this, yes, the mixer outlet MX, enter. Okay, now we combine all and see. then we can now start the pre-treatment of the whole mixture. So we can run this. Okay, so it ran without an error. Okay, so we have all of this here. Yes, so we can start the proper modeling now. Let me see. Now the first thing is to pump or to increase the pressure of this mixture. So it's mostly gas, yes, apart from water, I guess, that is in liquid. Let me see. What do we do? Okay, we can use a compressor. Let's use a compressor. Now compressors will not accept liquid, so I will detach H2O from here. Yeah, I think that's what I'll do. I'll detach H2O and then I'll probably heat it up first before sending it into the compressor. Let's see if that works out. So I detach this. Yes, destination. Yes, so I will detach this. Then I will pump. Okay, yes, detach this. Then probably I would heat it up to 100 degrees Celsius first. Okay, so I'm heating it up. Let's see. Hot H2O. I'll heat it up and let's see if it works out. Hot H2O. Yes, so this would be like 100 degrees Celsius, so that it's let's say let me see, 0.813 bar. Yes, 0.813 bar. So I think that's fully specified. Let me see. Yes, it's fully specified. Then yes, we can now connect this to this. Then I want to connect this hot H2O to the mixer as well. Okay, so this connects to this. Let's just connect it that way. Okay, yes. Okay, so all of this is connected to this mixer. Then we have our compressor outlets. So we have our compressor outlets here. So for compressor outlets, we just say pumped feed for the compressor outlets. Then we can specify compressor. We are using isentropic. Let's use 0.85 as our efficiency, isentropic efficiency. Then discharge pressure is 50 to 100 bar, right? 50 to 100 bar. So we can, let's say we use 60 bar. So everything is connected and we can run the model to see. Okay, so we have, let me see, we still have an error in B6. Okay, let me see. Okay, so I think I'll just I'll pump the water separately, right? To avoid any errors, any subsequent errors. I'll just pump the water separately. So I'm detaching water from this and we will only compress CO2 and H2 since they are gases. Let's see. Okay, so that's okay. So let me check this H2 stream. H2 stream has, let me see, Okay, it has CO and H2. Yes, so we are good to go, right? I can change this to Syngas now, since it's no longer just H2. So this is Syngas. This is Syngas. Then for H2O, I think I would pump then heat, right? So I'm going to pump this. I'm going to pump the feed before I heat it. So I would use a centrifugal pump. So we can move this forward a bit, or it's okay there. Then we can move this backward, right? Then pump it. I'll pump it to 50 bar. Let me see. Okay. Yes, pressure changes. So we are going to pump this feed, right? Okay. We are pumping it to about 50 bar. Then we are going to be heating it. Okay. Let me see. pH2. Okay. pH2O. Yes, pH2O. Okay, that's for that. Then let me see. This will come over here. Okay. Now we are using discharge pressure is 0. Pump efficiency is 0.85. Let me say 50.3. Then this is 0.85. Okay, so that's for this. Then we can now continue. So now that we are going to be pumping the H2O, I think it's best to keep this heater in front, so it serves as a heater for both the Syngas and then the H2O as well, right? So instead of just using it to heat the H2O, I would use it as the heater for both the Syngas, CO2 and H2O. So I will bring this guy forward. So it has been pumped, so we'll bring it forward and also add it as a feed to the heater, so it heats everything together. Then we can change this to let me see, this is now 200, or let's go with 250, within the range of temperature required. Then that's for that. Then I specified 50.3 bar. Okay, here I specified 50. Okay, 60. I will change it back to 50.3 so that they can be uniform. 50.3 bar here, right? Efficiency here is 0.852. Okay, then I would now specify outlet pressure. Outlet pressure is 50 bar. So you have about 30 kPa pressure drop, right? 30 kPa pressure drop. That is from 50.3 to 50 bar, right? That's about 30 kPa pressure drop. So with all of these, I think we can run the model to see if it works. Okay, so yes, it works without errors. So let's see what we have now. Let's see what we have from the stream results. Okay, so this is the stream results. We have 250. We have 250 degrees Celsius. 250 degrees Celsius. Then let's see. Okay, the pressure also. Yes, the pressure is 50 bar, right? So we have our operating conditions for the process already now, right? So we can now model the reactor. We can model the reactor to the process. Okay, so in this case I want to make use of a stoic reactor R-stoic reactor for this particular illustration. I'll make use of an R-stoic reactor. Okay, so we have the outlet stream. Okay, let's see if this works. Okay, so we have this, so we can align this as well, right? So we specify the conditions, the same conditions as the feed to this particular reactor. So this is 250 degrees Celsius, 250, then 50 bar, then reactor or reactions. You can add one reaction to this particular reactor. You have syngas to form methanol. So you have this, then you have methanol as the product, the only product. Then for component, I want to use H2 because H2 is smaller in amount in the feed. So I'll use H2 as my fractional, as my base component. Then for conversion, within 60 to 90%, I'll just use 0.85, right? 0.85 for conversion. Then CO is -1 for this. Then I think H2 is -2. Then methanol is 1. Yes. So this is the stoichiometry, and this is the reaction equation here. So everything is set up. We can run the model. Yes, and it ran without errors. So we can check the stream result. Okay. So from the this is the reactor stream results. So from the stream results, we have all of this. We can check the mass flows. So for mass flows, water and CO2 are inert. They are inert, so they are not part of the reaction. They are just there to boost the reaction process. Then you have CO reducing in mass because it's a reactant. Then you have H2 also. Then you have the methanol that is produced, right? So you have this amount of methanol produced, 1943.45 kg per hour of methanol, right? So this is the methanol that is produced. So the next step is to separate the methanol from the other products or from the other unreacted components, right? So you have to separate the methanol. So you can easily do that with your splitter. Just use the splitter to get that done in this case. So this is just an illustration. So you just use a splitter to get that done. So we have, let's say we have methanol. Okay. Let me see. We can cool down our reactor products first before we do. We can cool down our reactor products before we do the separation. So I'll just delete this for now. Yes. So first things first, what do we do first? We can reduce the pressure. Yes, we can reduce the pressure. Okay, let's cool down, then reduce the pressure. So we have, let's cool down back to, okay. So we have this atmospheric pressure. Then for the bar, we can use let's say 47.7, because we have a 50 bar. We have 50 bar as our reactor product. So we can check this to see how it goes. Let's see the stream results for pressure. Okay, yes, so 50 bar inlet, outlet is 47.7. So that's a pressure drop of 30 kPa still. So we can move this and use a valve. We use a valve to reduce the pressure to about close to let me see, this valve symbol is too small. Okay, yes, we can reduce it to close to atmospheric pressure, right? So we have outlets. Let's see if it works out. So we have P. Let's just use this. So we are using the valve to reduce the pressure. Okay, so outlets will be like let's say 130 kPa, right? So that's very close to atmospheric pressure. So 130 kPa, 130 kPa. So this is kPa. So we can run and see if it works out. Okay, so that worked. Now we can separate the products. Okay, there was something here. Yes, we can separate the products using the separator. So we use this to separate products here. Okay, so for this let our top be gaseous products, and then methanol can be produced from the bottom of the separator. Okay, let me just see. Okay, then we can have our so this is MEOH, or let me write it in full. So we have this. Now we can connect this to the inlet of the separator. Then what else? Okay, we can specify the splits. I would prefer to specify methanol. I don't know if it works, but let me specify methanol. So for methanol, you have this to be 1. Yes, 1. Then I think the others should be specified as 0. 0 for the rest. 0, 0, 0. Okay, so we have specified all of them. So I want only methanol to come out from the bottom. So does it work? Yes, I think it works. So we can also check the stream results of this particular equipment. Now we have this. Okay, so yes. Okay, so methanol comes out from only the methanol stream, which is the bottom of the separator. So we have all of this, right? And we have it at atmospheric conditions or near atmospheric conditions. Okay, let me see. Okay, so that's it. So inputs, let me see the input. Okay, so basically that's how it works. Okay, so I'm seeing we are having 8 degrees Celsius from what I'm seeing. Is this the separator? Nope. From the separator we have about 8 degrees Celsius. So I guess we can increase the pressure, right? We have about 8 degrees Celsius here. Okay, so we can adjust that by probably heating back to, we can heat back methanol to atmospheric conditions, maybe by adding, you could possibly add a cooler after this, sorry, a heater. You could add a heater to increase from 8 to atmospheric temperature, or we could try to manipulate the pressure, because I know it's the pressure that reduced that temperature. Yes, I think it's the pressure. Let me see. Okay, let me see this. Okay, we have 25 degrees Celsius here. Let's see the stream results. Okay, so it's 25 here. Now after this we have this, so this should have inlet of 25 degrees Celsius. Let me see, should have an inlet of 25. This, no, not the separator, the valve. I'm looking for the valve stream results. That's what I'm looking for. Okay, so it is in the valve that the temperature dropped to about 8 degrees Celsius. So we can use, maybe we can increase the temperature here, let's say 40 degrees, and then run, right? So we increase this to 40, and then we check the effect on this methanol. So let's see the methanol temperature. Okay, so it's about 15 degrees. Okay, so we can increase it further so that at least it gets to about 25 degrees Celsius. So I'm taking it to 60, and then I'm running again, right? I'm running again, and then I'm checking the methanol temperature results. Okay, so it's about 23, right? So if we take it to maybe 65, we should have it at atmospheric temperature, right? So at 65, let's see what we have here. Okay, now we open this, and yes, it's at 24.8. okay, so we can work with that, right? We can work with that. So yes, you have your separator, right? Separator stream results, right? So let me try to maximize the screen for this. So this is basically what you have. You have methanol at 24 degrees Celsius, 1.3 bar. So you can still decide to manipulate the process conditions further if you want, based on the flow sheets equipment. You can still manipulate this if you want. You can also try to work around producing more ethanol, right? So ethanol is produced from this particular stream of this separator, right? So basically this is how you can model methanol production, right? A methanol production process from biomass. So we have this as our complete process. How do I try to zoom in to actually make everything visible? Let me see. Okay. Oh, this is too small. But this is the process. But let me see if I can increase it. Okay, the process is quite large. Okay, so yes, it starts from here. So you have your biomass feed, right? Now if you haven't followed up with this, you can check the first two videos. You can request for the link in the comment section, and I will drop the link. So for the first two videos, we did the yield, the decomposition, then the pyrolysis, then you have the gasification over here, right? The gasification. So this is a yield reactor, a Gibbs reactor, then the gasification to produce hydrogen. Then we now produce hydrogen, but now this is an illustration for methanol production, right? So the biomass can also produce syngas, as the case may be. Now, when you have your syngas produced, you can use it to produce methanol subsequently, right? So this is the methanol production process, like a very simple, basic methanol production process. So you have your syngas, you have your inert components as well, H2O, CO2, just to be there to boost methanol production. So you pressurize your feed, then you heat your feed, then you send it into the methanol production reactor. Then you get your methanol products with the other components. Then you cool your products, you reduce the pressure, and then you separate methanol from the unwanted components, right? So basically that is how to actually model methanol production from biomass gasification, right? So with this, we have come to the end of this lecture. If you have questions or observations, if you want links to the previous videos on this, kindly indicate in the comment section, send in your questions and observations. Then like this video, share with your friends. Also subscribe to this channel for future notifications on process modeling. Thank you for joining me in this particular tutorial. Do have a good day.